pleasure to introduce Eulalie Boucher from ECMWF, and she will talk about end-to-end observation-driven weather prediction. So we're looking forward to your talk, and yeah, please go ahead. You have 20 minutes.
Yes, so thank you, Tobias. So I'm Eulalie Boucher. I'm presenting today on behalf of a group of colleagues at ECMWF, and I will share the work that we're doing at ECMWF on end-to-end observation-driven weather prediction with a system that we call GraphDOP. Okay, so at ECMWF, we're actively exploring multiple paths for integrating machine learning into weather prediction. So one of these is to include some machine learning aspects inside the physical model. And alongside this, we have a key approach, which is, of course, the development of a fully data-driven model like AIFS and AIFS Ensemble, that are models which are trained from reanalysis like ERA5 and then initialized from operational analyses. And then we have a third strand of research, which I'll focus on today, which is a newer and more kind of radical direction, which is directly using observations for weather prediction, so without any NWP data in the loop. Okay, so for some context, there's been a machine learning revolution in the last years in weather prediction. These models are trained and initialized from reanalysis and analysis. So they use atmospheric states at time t and t minus 6 hours. And they are trained to forecast the atmospheric state at t plus 6 hours, so into a future analysis using a combination of graph neural networks and transformers. And so at ECMWF, the deterministic version of AIFS has been implemented operationally on February 25th this year. And actually the Ensemble version is also operational now, so all new from last week. And so these models, they produce very accurate forecasts. So for instance, if we look here at Z500 forecast scale at multiple lead times, we can see that AIFS offers like a promising alternative for medium range forecasting. However, AIFS is trained and initialized from IFS analysis, and therefore it still relies on traditional data assimilation. And so we can kind of ask ourselves two questions. So one is, will the skill of these machine learning models hit a ceiling, being the ERA5 kind of scale ceiling? And two, if we think of weather prediction as being an initial value problem, can machine learning help us to improve these initial conditions and then reduce the forecast errors further? So traditional data assimilation systems like 4D VAR, they are very powerful, but they do have some limitations, notably in the observations they are able to use, because 4D VAR, for instance, only assimilates around 5% of the observations. That's mostly due to thinning that will enforce spatially and temporally uncorrelated observation errors, but it's also because it can only assimilate observations which are sensitive to a well-modeled physical process, and for which we have a good observation operator. And there are also many approximations such as linearity, Gaussianity, or specification of observation and background error covariances, etc. And so in the end, there's a lot of rich information that are present in the observations that are not yet exploited by current DA systems. And so all of this has kind of led ECMWF to propose and explore a new paradigm, which is what we are calling here AI-DOP, so direct observation prediction, which I mentioned previously. So the idea here is to have an end-to-end observation to forecast model where there is no analysis or reanalysis involved. So the model will learn to map directly from the observations to the forecast. Effectively, it's building its own internal model of the Earth system dynamics during the training and solely based on observations. So the kind of high-level architecture of this model is to have encoders that will map the different observation types to a common representation in what we call a latent space. This latent space will then be a representation of the atmosphere, and then it will make a prediction using the observations as the truth. So again, there's no NWP or ERA5 data in the loop. The model is really trained to make predictions of observations at arbitrary locations and times. So So after the prediction, we will then decode back out to observation space. And in principle, the observations that we can use can include kind of any observation type, including those that have not previously been used in DA systems. But of course, a limitation of the DOP concept is that we can only predict variables that are observed. So for instance, we're able to forecast snow depth or precipitation, but we wouldn't be able to forecast, for instance, sea ice concentration, for which we don't have really in situ observations for. So here we have a more detailed diagram of DOP. So this one is graph DOP. So this network is based on graph neural networks. Graph neural networks are able to handle kind of irregularly spaced observations, such as satellite orbits or in situ observations. And so the idea is that from a 12-hour input window, we take all the observations that are available, and we dynamically build some graphs at the observation points, and then we embed each observation type into a common latent space. This latent space lies on an 096 grid. And this latent space will represent the state of the atmosphere. And we then have the main kind of network, which is a transformer with window detention, that will learn to advance this state into the future. And then using graphs again, we will decode back out to observation space in the subsequent 12-hour window. And then we can autoregressively roll out the outputs back into the inputs, etc., to create a medium range forecast. So for this network and to train the network, we're using both satellite observations, so geostationary infrared, polar orbiting, microwave, infrared observations, radar, altimeter, etc. And also, of course, conventional observations, so synops and radiosondes, buoys, etc., that give us the real weather parameter that we're interested in. And so the network is trained to forecast both of these. So we have then forecasts of both satellite observations and of in situ observations. So for instance, here I'm showing a 5-day Severi forecast. Yeah, now you should see it moving. So it's a window channel on the top row, and on the bottom row we have a water vapor channel with graph DOP, so the forecast being on the left and the true observed brightness temperatures are on the right. And we see that although the prediction is slightly smoother on the left, that's due to the mean squared error that the model is trained towards. But apart from this, we are forecasting the correct dynamics. For instance, we see the convection building up over Africa in the correct places and the correct timing. In fact, we've even seen that the convection diurnal cycle from graph DOP forecast, which was much closer to the one in the true observations than, for instance, in the simulated observations from the IFS. This is another example of a satellite observation forecast. So here it's a 24-hour prediction of a Yazi window channel with graph DOP being on the left and the observed brightness temperatures on the right. And again, we can see that a lot of the features are present both in the prediction and in the observed observations. And for instance, we have this spiral-shaped cloud, or here the convection over the French Pyrenees. And we've also seen, so looking at the forecast of the satellite observations, we've also seen that graph DOP is able to correctly understand and forecast some more kind of precise or difficult signals in the brightness temperatures. So for instance, here we are looking at a rapid freezing event in the Arctic in October 2022. And we're looking at microwave observations, so AMSR 2 channel 5 brightness temperatures. And so the top line here is a 12-hour forecast. So on the left, it's a graph DOP forecast, and on the right, we have the target or the true observations. And in orange here, we see kind of the signature of sea ice in the brightness temperatures. And already this is quite nice to see in a 12-hour forecast, because it's a strong indication that the model has correctly encoded the relationships between surface emissivity and measured brightness temperatures into a coherent latent representation of sea ice dynamics, and that it's able to reconstruct it correctly in a 12-hour forecast. But what's kind of even nicer to see is that if we look 10 days ahead, so 10 days later into the forecast, we see that GraphDOP was able to forecast the signature of sea ice growth in the brightness temperatures quite accurately. So it managed to combine the initializing observations with its learned representation of the Earth systems to then infer that the atmospheric conditions at the start of the forecast were favorable for freezing to occur. And it has correctly done so in the correct places. So, for instance, here we see, if we compare to the first panel, that the sea ice has effectively grown, and in the correct places and in the correct timing throughout the 10 days. So now that we've kind of seen that DOP is able to forecast satellite observations, we can move on to the weather parameters that users are actually interested in. So again, as I've already said, DOP is trained to forecast towards the true observations only, so towards sparse in situ measurements. For instance, here we see the input observations for 200 hectopascal winds at a given time. And during training, we would train towards a similar spatial coverage of these same observations, but 12 hours into the future. But once the training is over and once the model is trained, we can actually ask the network to forecast anywhere. So we're able to create kind of a global gridded forecasts. And we can do this even in places where there was no direct observations for that parameter. Again, this gives evidence that the model has developed a true model of the relationships between the different observations. And so ultimately, we can create these global forecasts for kind of all parameters that have been observed. So for instance, we have T2M, T850, U200, SST, Z500, but we can also do it for satellite observations. So for instance, here it's Channel 9 from Siberi. And so with these global forecasts, we can look at kind of specific case studies. And one that's interesting is here of a hurricane, so an extreme event. And so we looked at Hurricane Ian. Hurricane Ian occurred in September 2022, and it went past Cuba, Florida, and kind of North Carolina. So we initialized the forecast on the 24th of September 2022, and then we have a look at the track of the hurricane over several parameters. So this means that for several instruments that DOP is able to forecast, or several parameters that DOP is able to forecast, we asked for a gridded forecast, and then we compare them. So firstly, this allows us to kind of analyze DOP's internal representation of the hurricane and how it sees it and how it sees it evolve. And secondly, it's also good for us to check whether there is kind of consistency between the variables that are forecasted. So for instance, on this slide, we're showing the wind speed over the course of 6 days. So the top row here is the GraphDOP forecast, and we're comparing this to ERA5 on the bottom. And we can see that in general, the advancement of the storm is pretty much in line with ERA5, with the exception here of here on day 5, where GraphDOP seems to have kind of overestimated the speed of the storm a little bit. So it's lingering, yeah, it's moved east kind of quicker. But we can also see some very fine details in these forecasts, such as, for instance, in these first panels, we see the eye of the hurricane, which matches quite well the eye that we can see in ERA5. And what's nice with DOP is that we can forecast variables across the Earth systems. So, for instance, we have variables over the ocean as well. And here we're showing the significant wave height forecast. So that was trained using radar altimeter observations. And we can see again that the advancement of the storm is pretty consistent with ERA5, except again here at day 5, where we have a slight difference. And so here we see that DOP is showing a bit less strong waves than ERA5. And what's nice is that this is coherent with what we've just seen before. So in the wind forecast, since DOP had overestimated the speed a little bit, the strong winds weren't blowing over the west coast of Florida for so long. And therefore, not as many waves have had time to develop here. And we can see that quite nicely in the wave forecast as well. And if we look now at the SST response, we also see some nice cooling that's happening in the DOP forecasts here in the first like kind of starting actually from day 2 onwards. And this cooling is due to wind and wave ocean mixing and also cold water upwellings. And we see that DOP was able to really learn the relationship between all of these factors when being trained exclusively on in situ observations. And in fact, we don't really see this cooling in ERA 5, which is shown on the bottom here, until day like 6 or 7. And that's probably because conventional real-time SST products, which are used in ERA 5, find it difficult to detect cold wakes from satellites, as the area of the storm is usually obscured by thick clouds. But we actually see that DOP is pretty much in line with the SST anomalies satellite level 4 product that we are showing here, which shows already some cold SSTs from day 4 and then continue to advance until day 7, where it's pretty much in line with the graph DOP forecasts. So next, I want to share with you some of the latest kind of headline scores that we get when we evaluate these global forecasts against in situ observations and how they compare to the IFS or AIFS. So firstly, I'll show some summer season Northern Hemisphere scores. So these scores are for June 2022. And so here we're showing the RMSE here on the y-axis versus the lead time, so day 1 to day 10 on the x-axis. And we show in blue the IFS on an 096 grid, so keep in mind that it is a pretty coarse resolution grid. And in pink, we have graphed up on this same grid. And then it's the RMSE between the gridded forecast and the closest in situ observations. And so we see that for 2 meter temperature, for a surface parameter, we're doing pretty good, especially in the shorter range, where we are already kind of outperforming the IFS in the short range, and then we catch up but remain competitive in the medium range. But for the upper air here, which I represented by 200 hectopascal wind speed, we can see that we're not far behind, but we still have a slight disadvantage with regards to the IFS. And we can notice that both curves start to flatten out a bit here at day 8 or so, and that might be due to some excessive smoothing. So we still need to have a look at how we can limit that. And so moving on to the winter season, so here it's January 2023, for which we also have here the AIFS scores in green, again on the same 096 grid. Here we can see that the scores we have are a little worse than they were for summer, but again, we keep this advantage over both IFS and AIFS in the shorter lead times, especially for the surface, so 2 meter temperature. And then we kind of catch up and remain competitive. And for the upper air, we are still lagging a bit behind, especially in the winter months. And so we think that the difference between the scores that we're getting in the summer and in the winter months are at least partly due to the snow misrepresentation. So this model version, we did not yet have any snow observations in the model, so we hope that adding these snow observations and better modeling that will help to bring the scores down in the winter.
2-minute warning.
And so lastly, because I think I have a few minutes left, I wanted to touch on some sensitivity tools that we are working on to study like the physical consistency of graph DOP. So for decades, the FSOI tool has been used, for instance, in the IFS, and the idea is to estimate how every observation has contributed to reduce the forecast error. And we can do the same actually for graph DOP, since we have the adjoint of the model using the backpropagation that we used in training. So on the left-hand side here, we have kind of all the main results from this. So on the y-axis here, we have all the input channels that go into the model, and for each of these channels, we compute how much this specific channel has contributed to reduce the forecast error after 12 hours. And so if we're on the left here, it means that the channel is reducing the error, and on the right, it means that the channel is actually increasing the forecast error. But so as you can see, kind of a good news is that 95% of the channels are actually working together to reduce the forecast error, which is reassuring. Another tool that we can, or another thing that we can produce with FSOI is produce some maps to find out really the location of the observations that are the most important to reduce forecast errors. And that's something we've done here for 2 ATMS channels. For instance, on the left here, we have a water vapor channel, and we see that it's mostly observations over the ocean that are reducing the forecast error. And on the right, we have a humidity channel. And for this one, we can spot kind of these 2 areas in which the observations seem to be the most useful. And these actually correspond to observations that were the latest in the input window, so the closest to what DOP has to forecast. So in fact, it's quite similar to what 4D or VAR would do, where it would put more weight on observations at the end of the assimilation window. And so this kind of tool is really important because it then allows us to fetch expert knowledge from experts on each observation types and to get some feedback and help us develop the next graph DOP update. And so to quickly summarize, we're exploring the extent to which a fully observation-driven end-to-end weather prediction model is able to challenge the state of the art. And we're seeing promising results, such as evidence that GraphDOP has learned an internal model of the Earth system, including the atmosphere, but also SSTs and sea ice. We have the near surface forecasts, which are already outperforming IFS in the short range and are competitive with IFS in the medium range. But we also see that we have the upper air scores that are still lagging behind IFS, especially in the Northern Hemisphere in winter. But these scores continue to improve with each update that we make. We also see with case studies that GraphDOP is producing useful forecasts. And lastly, we have GraphDOP that's able to use observation types which cannot currently be assimilated by data assimilation systems. And of course, we have lots of scope for future improvements, which include incorporating a observation-based background or using more data sets with better quality control, and also training towards a CRPS loss, which should minimize the smoothing effect that we have. And thank you for listening. And we have a paper which is currently up on archive if you want to learn a bit more.
Thank you very much, Eulalie. A very interesting presentation. And I can tell from the number of participants today, 150 people are joining, and also from the number of questions asked in the YOPED, there's a huge interest in this work. So we will not be able to answer all the questions now, but I want to remind everyone, so please use the YOPED to ask your questions. And also a message to all of our presenters, feel free to go to the YOPED after your talk and answer the questions that we cannot address in the live Q&A. And also for other people from ISDA, you're also free to answer questions in the YOPED because this is a work done by many people, so you can support Eulalie. From the questions that I was reading during the talk, I will try to kind of distill 3 main things that appeared multiple times. The first one is, can you comment a little bit on the architecture? So what are you using? How large is the latent space? I think this is something that appeared in several questions.
Yes, so the kind of main architecture it's very close to AIFS if people are more aware of the AIFS kind of architecture, but it's basically some graph neural networks that will kind of map the observations to the latent space, and this latent space is a 096 grid, and I think currently it varies with the models, but I think currently we have like 1024 size for the latent space, but it's yeah, it's still kind of constrained by this 096 grid, and then we apply to that a transformer with window detention, as you can see here on the diagram. It's window detention that goes kind of around the globe like that. So that's the kind of main transformer, so the main network that will learn to first mix all the observations together, but also advance it in time to the next 12 hours. And then it's a similar graph neural network that will decode back out to the observations.
Okay, thanks. Then a question that I think appeared several times, and I can understand this because it also came up for myself when I saw this work the first time, is like, what are the limitations or constraints or opportunities from looking at the input and what you can output? So many people asked, okay, what are the limitations for output? And I think you also touched it in one of your slides, but perhaps you can, I don't know, try to give like a summary, or you can also go back to your slide and repeat it in different words. So
the kind of, yeah, the limitation mostly is that we need an observation to train against. So you can't forecast anything for which you won't have a real like in situ observation and enough of these. So for instance, for the like deeper ocean, we think that we may not have enough observations to fully model the what's going on in the deep ocean. But like for SSTs, using the buoys, using like all of these kind of in situ observations that we have for now seems to be enough. But yeah, you really need like these observations. So you can't forecast something which is coming out of a remote sensing like remote sensing product or a level 2 product or things like that. It really need like the observations. That's kind of the main limitation, but yeah.
okay, thank you. And then perhaps one last question, and I would kindly ask you to answer the remaining 15 questions in the op-ed. Are there plans to release the weights of graph DOP at some point? So people started asking if they will be like able to access this work at some point. Do you know this, or it's a very political question?
Yes, I think for now it's still very much research. So like the weights that we have are like changing every week even. So for now, I don't think it's in the plans, but there's plans to merge kind of the architecture into Anemoy, which is the kind of Python package that AIFS uses and which is open source. So that's in the plans in the like next maybe year or so. But yeah, for now the weights are still like are still changing, and there's also some like we can release the weights, but you also need the observations, and the observations are not ours to release, etc. So that's
thanks. Thank you again, Eulalie. Amazing presentation, and so we move on to the next speaker. Thank you.